this. So actually, we have one commercial fiber optic cable. It's similar like this. So this cable have 1, 2, 3, 4 components. The first one is the optical fiber member is in the middle, right? This one, component number 1. Then number 2 is steel. Actually, FRP strand member is yellow color. The 2 FRP strand member. Then number 3 is a jacket. LS jacket is a black color one. Then we have steel wire, number 4. So this cable, we need to test the pulling force and the applied force from the top. And we talk about more detail this later on. So second design, we add one more steel wire at right hand side. Okay. Then we try to test this one is the from the force from the top. We call cross-sectional force. Okay? This is the wire. This end and this end 50 cm for whole fiber optic length. Then we apply the force from the top with different width, right? 5 cm, 10 cm, 15 cm. I don't know able to do it very well or not. Second one is the pulling force. Pulling force from both ends of the cable. This is the end. One end is like this is what here. So this end and this we pull. The total length of the cable is 50 cm. So we try to do this in the simulation. After that, in the lab, right, we'll cut 50 cm also. I don't know how to do it. Maybe, we'll figure out. We pull from both ends. See when the cable will be broken or what, or we can't detect any signal from the measurement component. We'll figure out how to do it, or you have any suggestion you can give us. This is what suggested by Dr. Gafford. He said he can do something like this, okay? Pulling force and the force from the top. And for the every component, we have find out all the dimension and also the mechanical properties already. I let you know. Go through this. This is what we have. So we go to one by one. This is all the resource. Okay, so first one, optical fiber member is in micrometer. So this modulus elastic we have. Poisson ratio is a must, also need to do it. And tensile yield strength is a must. Last time you said have to use it. Tensile strength, some have, some don't have.
Why the value like you have M1, 2, 3?
Oh, I see. This one have, this one fiber optic I have 3 layers. So but Dr. Capo said that inner layer C1 is too small already, so we just combine use M2 and M3. Consider this a solid core. So C3 is a coding. So yeah, C3 is coding, so it's 242. We just take 242 only, plus minus we just ignore. It's too small, so this we have too many. Okay, then so we take the modulus from this, okay, 1.035 for coding.
In the M1 and M2, both of them we can put it as the same material because you see the not much different also.
Yeah. That's why it's suggested by Dr. Gafford. So we assume that M1 and M2 also is same with M2.
But M3, what is the material? I see the Poisson ratio.
Yeah, it's 0.35. I don't know what is this, but it's something like coding.
And then the coating is quite soft. You see the young modulus, it's just like 1 gigapascal. 1 gigapascal is quite high. We cannot ignore also.
This one, you mean is soft, right? It high mean
It's not really
harder.
so soft, but compared to the glass is harder.
I see.
If 1 gigapascal quite hard, I mean compared to normal plastic materials, is considered harder than most of the plastic materials.
I don't sure about this also. I'm not expert in this. Maybe coating is to protect the glass. I know. But how about the Poisson ratio? If high mean what or low mean what? Any insight from this value?
They want just used to predict how is the deformations from like two directions. When we stress it, so like for the cross section area, it will have x and y axis. How much is deformed? So this one is used for calculation to predict how is the deformation happens if we apply load.
Okay. Never mind. It's okay. So let's proceed. So first component we have all the information already. Then second component is the FRP strand member. We have the diameter also 0.46 mm. The modulus of elastic is this one is 200 GPa. Then tensile strength we also have this also, and the tensile use strength for deform is we have one range 276 and position is 0.35. Marine, which number did you put? 276 or 517?
276.
Okay. So this. So be careful. All this unit is giga PA. So when you key in, I don't know, make sure it's correct. How many zero behind? This you have to take care of this. But this one, actually, last time also it's not confirmed one because you get it from this one is the steel marine. You remember? It's FRB. But as Dr. Gafford said, you have to try to find the actual value. You can try to figure out in the future. All right, Maureen, can you hear me?
Yes, sir. Sorry, sir. It was
Take note on your book. This one is have to change in the future. Modulus of elastic. This one also actually this one is for steel. You see, 200. Never mind. We just maintain this first. Dr. Gafford also mentioned that you have to try to figure out adjust this number in the future maybe. Okay, then this Poisson ratio 0.35 is FRP member, so this one is correct, 0.35. Okay, then the jacket. Dr. Capo said the LSZH, low smoke zero halogen or what jacket is similar to MDPE or what? So what MDPE? So what value that you get?
HDPE or MDPE?
MDP, medium density polyethylene, sir.
Okay, so what is the value? Do you still remember?
I got Young's mod, the tensile modulus and tensile strength.
Yeah,
and
what is
density.
do you remember what is the value?
For tensile modulus, it's 172 MPa.
172 MPa. Is it?
Yes, sir.
This one is get from the supplier. So what do you get the different one? What is the value that you get?
Why the value is so low for the tensile strength?
I got it from Wikipedia, sir. Like when I searched for this material for LSZH, I didn't get any value. But when I searched for MDPE, I got it from.
Yeah, what is the value for this and this?
Modulus.
No, Marine. So you just get the modulus elastic. How about MTP?
Tensile,
Tensile
uh,
strength of MTP.
for tensile strength, it is 12.4, sir.
Sorry,
12.4, sir.
12.4
MPa, yes, sir.
MPa. Make sure you need is correct. So it's
And also the
similar.
density,
Sorry,
density also, sir.
density.
Density is 0.96, sir.
Density density.
Like when I edit the material in the material thing,
Yeah,
there
yeah.
is
Why the density? 1 point.
0.926
So what is the unit?
gram per centimeter cube, sir.
How about the Poisson ratio? Do you get this?
No, sir. Poisson ratio, I didn't get Poisson ratio,
So
sir.
this one.
The Poisson ratio, maybe you can check for the Poisson ratio they use for polyethylene. I believe mostly is same lah.
Okay, sir.
Polyethylene. How to spell?
Polyethylene, POLY.
Okay,
Yes,
you find out this polyethylene. Because as I know for the simulation, we need the tensor yield strength, right? So that we have the we need to have the figure like this last time. Dr. Kui showed to us so that we know the maximum value. Here, right, use strength to compare whether this one is higher than the maximum one. This one is I just print screen. This one is the yield strength that we set in the simulation, correct? This value.
Yes.
Dr. Kui, correct, right?
Yeah.
We key in the value and we show here the maximum, the yield strength, the deform plastic deform value one. So this one don't have, maybe we don't know the result. This one have to figure out also. If anything, correct me. I'm wrong. Okay, then number 5 for the steel. Steel is galvanized steel. What we have is good galvanized steel 200 GPa. Is GPA. Then tensile strength 1570 MPa. Poisson ratio 0.29. Tensile yield strength also don't have. Do you get it? No. This Marine?
Sir?
Do you have this information? Tensor yield strength?
There are values, sir, but for each steel it is different, sir. There are steel named as steel mild and chromium vanadium steel and steel margin steel. So I don't know which steel to choose.
Maybe later you share to let us to know lah. You share your screen later on to.
I searched for this, but I got many values. That's why I
Is
didn't.
this one? Last time you shared. Not this one. New information, right?
No, no, sir. This one, like
This
this
one is
week only, I
this one is
use
okay. Never mind.
old one, yes, sir.
Maybe you let us know later on. You share to us. Okay. So far, what we have is this all information. Some is don't have. So today the objective is hope Dr. Kui can give suggestion how to simulate the pulling force this side and this side. I don't know which one is fixed fixture because I have to fix let's say we fix this side, you apply the pulling force is correct or not. You got to fix already, then you cannot pull right. I don't know. I'm not sure about this. Or fix up top one or down one. I'm not sure about this. This is 50 cm and how to apply the force from the top but with different cross-sectional area. Cross-sectional area mean like this. This is the cable. We apply force this here. Let's say 5 cm. Then we increase 10 cm and so on. The whole length of the cable is 5 cm. we also try to cut a no, if 50 cm, if 50 cm is whole cable. So we try to cut the cable, then we try to do the same thing in the lab also. In the lab, we only try to do the experiment for single steel cable. Let's say in the lab, we find that, let's say we apply certain force, the single steel fiber optic cable will be broken, then we consider that our simulation is correct. So from here, assume that our double steel design also can be used, something like that. This is what suggested by Dr. Gafo. So that's why we need to do the simulation. Same for the pulling force. We pull this end and this end. We try to pull it in the lab also. Let's say we pull in some extent it's broken or the fiber optic cannot function already. So we compare to the simulation. To some extent, maybe it start to deform more than the sensor used. Then we consider the simulation is correct. With the lab testing, then you have to prove like this. Yeah. Dr. Pui, anything you want to say?
My concern is for pooling should be okay, but how about you say you want to apply force from the top?
Yeah.
Then we consider a bending. So bending, they have many type of bending tests.
You mean
So
in the simulation or lab test?
I mean, in the lab also, in the simulation,
Oh.
what kind of bending you make? And then if for lab, what kind of setup that you can bend your fiber optics? Because I see that what you need is around how much? 5 cm.
This one this the length is I don't know. This is a suggestion only. Let's say I don't know. It can be 5 cm, it can be 20 cm, or because you want to do analysis. Because
your fiber optics is kind of like soft cable.
quite a soft cable.
When
Very
you
soft.
apply this kind of bending, it show you anything?
You mean you mean from the concept is like this. I don't know. You mean show me anything?
But my concern is for simulations is no issue. I mean, it's just a virtual condition. You can set anything you want, then you can have the finding. In the real experiment, the physical experiments, how you going to
observe the difference?
How you going to do these experiments? Pooling, pooling could be okay. Maybe we can figure out something they can attach, then you just pull until it breaks. My concern is about the bending part. How are you going to hold the specimen, make sure it's tight? It's not like, like a cable, it's just flexible. You need to make sure it's tense, then you apply the force.
So yeah, this one we also haven't I don't know, we'll figure out. For example, let's say you say can do the pulling force, right? So that means we can hold the cable like at both ends, right? Then we put something on top of the cable. Maybe something is heavy, different weight. I don't know. Both end we fix, then hold tight.
Let me search the figures of what we have.
Then we put something on top of it, different weight. 100 gram, 1 kilo, I don't know.
How we need to measure the force?
Force from the top. You mean the pulling force and also the force from the top, right? Also, right? I don't sure. So this one you haven't think about it. This is the idea from Dr. Gafford. He said that in commercial, they just produce the cable. They said before they produce the cable, they do some testing already, but they just don't have the information how many force then it will break, it will broken or so on. something like that.
Let me share the screen.
Okay. So I have to stop straight first.
This is the, you can see what I'm sharing. The machine we have in the lab is from Instron. Then what we have here is like a gripper like this. Hope you can see. It's like a jar.
Oh.
And one of the problem is your cable is so tiny because the clamping force of the clamping force itself is quite big lah. The force means if your cable is so soft, first concern is when you clamp it. When clamping already will damage your sample. Damage your fiber. You haven't tested, once you clamp, probably your samples is like you're using plier, you just clamp it with very strong force because you want to grip it and pull. So because fiber optic, as we know, made from glass.
The jacket itself is some kind of plastic. I don't know. The jacket is
it's
just a wire, like a wire in the lab. I think similar. I don't know.
Yeah. So I'm not sure lah.
That's wire in the lab.
Clamp the wire. If you clamp the cable, the fiber optic cable, the first thing, make sure it is not break at the clamping part.
Oh.
It's not break at the clamping here. Maybe I can show. I can search for more figure to let you see.
So this is a challenge, clamping part.
That is a challenge. Clamp. It's kind of this kind of clamp. We can tighten it. This one we have in our lab.
Oh.
So we need to tighten it, and then the clamp force actually is quite big, because when we clamp some plastic material. The plastic material you can check on the surface is like it forms some dimples.
Oh.
Because you want to make sure it have a very strong forces to grip to grip the specimen. You won't let the specimen slips when they're pulling. So maybe if what happens is, let's say you have your specimens, you clamp somewhere here, So if most probably this one it will damage. Maybe it will break somewhere at the clamping zone here. So this one it won't give you a good result. I mean the result is not it's not fractured by the force, it's fractured by the clamping of these things. And then, okay, another one, this one is the other type of clamping one, but we don't have. Let me clear this. This one, they use for this a soft sample. They use this one without clamping, but you can imagine this one is some kind of soft plastic, but they like tighten it. They just roll it. For cable one, I'm not sure. This one is for soft sample.
In the lab, you have this.
We don't have this. We only have
the clamping. So.
And but we can solve it, but I'm not really sure whether it's applicable or not Or what we can do what we can do here. Let me sketch. Okay, maybe you have your this is your fiber. This is your fiber example. You can see. So maybe what I suggest, maybe if you don't want the gripper here for your specimen, maybe both end here we do a casting. I mean a plastic casting. We're using epoxy. You cast it like a holder But this one need to make sure your epoxy really I mean is really like stick the stemples. It won't pull out from this. It won't pull out from the casting here, the epoxy here. That means we can cast on the epoxy. Then when gripping, we just clamp on the epoxy. Then we pull it. Hopefully, it can break somewhere at the middle.
It's good suggestion. But how to do the epoxy?
That one we need to do a casting. I mean, casting.
How to do a casting?
Let's say we need to have we need to have a Tupperware or what, we just take a container, then you just pull in the resin, the epoxy, you mix hardener and epoxy, you pull in the resin, and then you put your, you take the fiber optic, you just place it, and then you hold for maybe for 1 day. After this resin, it will cure, become solid.
Oh.
Example lah.
Oh.
Or otherwise, what we can do is maybe what we can do, maybe we can, what we can do is like, maybe we need to think of like, we take 2 pieces of, I'm not sure what materials that you can find in lab, then maybe place your fiber optic at the middle. We place the fiber optic at the middle, and then we apply epoxy glue. We just stick it. But need to make sure lah, this one, the material that we use here actually is to like hold the cables, and also is to protect the cable from fractures lah. It don't, because of this grip force, it break your specimen. It's just like a holder to hold your fibers. And then for the band, this one, you can figure out lah how to do this.
You can figure out.
But the problem is the bending one.
Yeah. So bending one so far.
Let me check.
So how to do the experiment? Bending.
We call it fractural test. Okay, they have many types lah. What we have in lab is identical with this. This we call it a 3-point bending. Maybe this one. This one here, we call it 3-point bending. Because the material we test, actually the material is very solid and rigid one. I mean, it's not like cable soft one. Then usually we cut the specimen in rectangular form. The size is about like this. Rectangular form with certain thickness. Then we place on top. These 2 here is a support. And then we must know what is the distance here lah. Then we place on the top. On the top here, it will apply force. It will apply force, and then the specimen, it will bend until it fractures.
So far, our cable only the width is 5 mm only. Thickness is 2 mm only. Just a wire.
Your wire is kind of something is soft.
Yeah.
When you apply force, maybe the force just very little is already bent. Maybe it will extend and then it drop until here.
Yes.
You understand what I mean, right?
But our concept is actually this one is the wire is applied on the very hot. It's a, I don't know. Last time can you all add on something? That means we want to implement it on top of the table, something like that, or what? Actually, we assume that it's very hard. At the bottom of the wire is hard surface, is it?
Oh.
Is correct or not, Honya? Merlin, do you also remember?
Yeah, it's correct. So below there is like we put something there. Not, it's not like a free fall. It's something like because the cable is in the soil, right? So there should be.
So the cable is in the soil. We assume that maybe we can test the different cross-sectional force, 5 cm, 10 cm.
Yeah. Something
so
like that.
how will affect the cable?
Okay, that means this is your table. So you will place your cable on top here.
Let's say
then on the top here, so you will apply force.
Yeah. Different.
Apply force at different sections.
Yeah, cross section. 5 cm width.
What is the point that you apply at different cross section? Similar.
This one not confirmed yet, right?
Not confirmed yet. Just for more analysis only.
This point also.
A whole point also can. Whole wire also 50 cm also can. It's just for more analysis because our report
for more analysis. And like depending, like for example, the length is 5 cm. So maybe if if we apply the force at different length, like we apply force at 1 cm, 2 cm, 3 cm, I believe the braking will be different, right? So that's the thing, we haven't confirmed on that yet.
I mean, the force for me, from my point of view, is the force almost similar lah. If they
It's
make
almost
the same material,
okay.
but how is affect your fiber optic reading? That one I'm not really sure.
Yeah. Because let's say we have wire, like, or fiber optic wire we put in the soil, like, it's different distance, like, different distance have different force. So maybe we know which portion will be broken first, because at different. Let's say you just apply the same force at the one point only, that point will broken, man.
Because hard surface and soil is different. Soil is some kind of soft surface.
Yeah. So it's difficult to really 100% imitate the actual condition. Just try to do something simulation or experiment so that we can compare lah. The main purpose is like that. We want to make sure that our simulation for single steel, let's say we apply certain force, it will broken, right? Then in the lab also same, to prove that our simulation is correct.
Okay.
To support our second design, yeah.
Maybe one suggestion is something like this. You guys think whether is it logical? So now we are comparing one steel and two steel, correct?
Yes.
So can we use the same testing environment? So saying like, so for both testing environments, say, okay, yeah, under the same environment, so this is the force needed to break two steel, and this is the force needed to break one steel. So two steel is better than one steel, something like that. Is it something logical to do test something like this?
Can. It's logic, but definitely you put two steel, confirm is higher lah.
Yeah.
Without any testing also.
Hypothesis.
Confirm is higher.
Yeah, hypothesis lah. That one is hypothesis. So the third one, is something that we are looking for?
Yeah, something like that. But last time we mentioned that you need to have some force at least is similar to the force for the landslide also, like Merlin had to figure out what is the force normally for landslide. It is Dr. Kapo mentioned that, like, had to figure out what is the force,
Like how much does the fiber withstands the force, like with the two steel and with the single steel?
Yeah. You also have to know that what is the force for the landslide happen. What is the force? How many Newton? Do you remember that? Dr. Kapo also asked for this. True or not, Dr. Hunyap, I forgot.
Yes, it's correct. We have to know the force first.
Yeah, you have to know the force of the landslide. If let's say the landslide force is 100 Newton, but your cable, even single steel cable, only can withstand 15 Newton. So no point, right? How you apply the fiber optic cable in the landslide determination. That's why Dr. Kapo, let's say your single steel wire only can withstand 50 Newton, but the landslide is 80 Newton. But you design double steel, in the simulation, show that it can withstand 100 Newton. Then you can support your work. Understand what I mean? Marie?
So, but there is no particular force that is for landslide. I didn't get any like approximate parameter for force, like any numerical thing.
How about I ask like this? Is there any, I mean, from your findings, or from your teaching, is there any work done before to test the fiber?
Yes.
Test the cable.
Yes, sir. They have placed like a slanting board. In the slanting board, they have placed soil, and inside that the fiber will be placed. So when the slanting board is like 40-degree any angle, they'll be changing the angle so that there will be a slight move in the soil.
What are the variables involved? Is it just the angle, or they are? I mean the.
Yes, they have calculated the angle or the angle, and also the displacement of the fiber from one place, the actual place to the other place. So when the soil moves, actually the fiber, it sends the movement.
Okay, but
and
I'm
the force
referring to a test that are related to the strength of the
force.
I mean a test that relate to the strength of the cable itself. Any test like that done before?
Strength.
You also don't know yet, lah. Never mind, Marine. You
Maybe
go
we'll-
back, you do some detailed review on this. At the
Yes,
same
sir,
time,
but
you do the simulation, you find out this information.
so far what I have studied, I didn't get the force. Like the force is something like they didn't have any force or something. So
This is
only
what
the
this is what we want to know, lah. Something like, for example, like the angle just now you mentioned, maybe perhaps different angle drop the soil. You are dropping the soil at different angle, maybe can cause a different force. I'm not sure about that.
yes,
Something like that. Is there any? Maybe we need information like this. Is it? I'm not sure.
Never mind, Marine. Don't bother about this. Just you try to find the information. If you have this information, it's very good. Okay. If you don't have, you try to develop the graph in the future about this.
Yeah, maybe later we try to ask.
Don't feel negative first.
okay, sir.
Everything you have to feel positive, thinking positive, then try to figure out how to solve this problem. At the end, we can't solve this problem, we can tune to another way to do it. Okay, the best way we get this information first. If no, then no, never mind lah. We just go on lah. We just compare to steel, single steel, double steel. Of course, double steel is better than single steel, and we just continue the research, okay, without knowing the maximum force of the landslide. Okay?
Okay, so from my side, what I can contribute you? I mean, what I can
Yeah,
do.
so Dr. Kui, so you said that let's say we put the table on top of table. So how we do the experiment? Let's say we support at the bottom.
Yeah, let me out of whiteboard.
So it's possible.
Okay, so your cable, we just assume the shape like this. Just assume the shape like this. So just assume that your cable is like this.
Yes.
So if you want to apply for
Cross-sectional force from top.
if you want to apply, I means if you want, okay, pulling first. Pulling is okay. Just mean one side, maybe.
This one you mean the simulation, right?
The simulation. Okay,
Oh.
if you mean what you can do here, maybe one of the side here, I mean this face here, the whole face, maybe you can apply as fixed support. That means something is fixed. So the opposite end here, the face here, you can apply as a force. The force, maybe you're going to have a direction toward here. Understand?
Oh. So that means we just pull one side is same as well.
Yeah, one side, one of the face, the bottom here will be fixed. The other one, but you need to remember, you need to select all the face, because the figure that you attach in WhatsApp, I saw you just only select certain face. So you must make sure.
Yeah, later on, Malin will show her simulation. Maybe you can double check again.
Yes, sir.
You just like make sure all the face, all the component that you select at the bottom. Example, you select the bottom face, you need to select all. On the top here, top face, you just select all the face on the top. Then one side you apply as a fixed support, the other ones you just apply a force. Then how much force? The one is depend on what what the force that you find in the litiges.
My question is, so in the experiment with the lab test, right, we pull both sides, both ends, right? So in the simulation, we just pull one side, it's same effect, right?
What do you mean?
You mean
No,
in the
okay.
in the experiment, in the lab test, right? We pull
In the lab also, we
both
don't
sides.
pull both directions.
Oh.
In the lab, just now you see one jar at the bottom, one jar at the top. The
Oh,
bottom one is static one, it won't move. Only the top one it will move.
I see.
Yeah, so that's why at the one of the bottom face, we just assume it is static, it won't move. So we call it a fixed support. So the opposite face, so we will assign a force where the force is like pulling upwards.
I see. Okay.
So this one is just for pulling. So pulling, not much, not much. I mean nothing lah. Just after that, you just observe. So maybe the stress, it will happen somewhere here. Then it will show you what is the maximum. The one you can check later on lah.
Okay.
Check on the graphical result.
Okay.
And for that one that you want to place on the table, right? So your specimens, okay. We just view from here. Okay, so for your specimens, maybe I just redraw it. Okay. So from this side, we will see like this, right? So let's say you assume it, you place on the table, means the bottom face here, this face here, you need to select as a fixed support. You need to select as a fixed support. Then, because you want to have a different cross section, just now Dr. Man say you want to have maybe you want to check here. Then after 5 cm, you want to check what is the force applied here, then here. Okay, so for this one, so maybe you need to sketch a line. You need to sketch a line and just assume this is your model. You just sketch a line on the top. When you select, you don't select the face, you select the line. You select the line on the face. So maybe you can sketch different line at the particular location that you want to test. You want to apply the force. Just sketch line. Line is just like a marker lah. Just a marking.
So let's say so let's say I choose 2 lines in the middle. So they will assume that apply the force within these 2 lines.
I think it's like that, but I never tried this before lah. For my opinion, I will try like this. Just put a line.
Okay, never mind. Marine will. I have a few concerns only about simulation. Later on, Marine will show you. First, because our design have different material so when we select the section that you mentioned, I select all the thing. Okay, is correct. We can select all the different material. The cross sectional have fiber, fiber optic, have a jacket and so on. We select all then we can pull like this. So it's correct, right? I don't know whether it's correct or not. Last time you mentioned have to do some something like connect all the material together. Similar like this. Last time you mentioned about this. I don't know if we don't do that, the simulation is correct or not. Last time you mentioned about something like this.
That one is because
this
have
one.
different materials.
Yeah, connection.
Yeah, you need to declare what is the connection.
Let's say we don't declare this. Just now you mentioned that you want Marine to select you can select this and select this together. Can I click, then you apply the pulling force. Let's say we don't select connection, we apply the pulling force. Also, can I don't sure about this. This is my question.
Yeah, if you have different material, you did not set the contact, right? So it will assume because they have some kind of like adhesions between them. So this one also very hard to determine the value or what. Yeah.
Just assume only. Let's say we don't select the connection component, so it's totally wrong, right?
You will see the result from what I show. I mean, you show here, right? It's just like peel off. These two material, it will separate at the interface.
Because what we want, let's say we in the lab, right? We pull up a certain force, a certain part will broken, or red color here. So I want as close as possible as actual one. I don't so let's say this one is I know this one is in integration. What is the maximum stress, right? So let's say with different material, how I know the overall maximum stress, or we just can check one by one. I'm not sure how to compare the result of the simulation and the lab, because I'm not this field. I don't know. Let's say with different
The lab
material,
one,
yeah.
yeah, it's quite difficult. That's why I say it's quite difficult. So
Yeah.
for the lab one, what we know, we test also, it's not like 100% accurate also, because the first thing, how you going to get the actual cross-section area? Because we only assume the cross-section area. We not do the actual measurements.
Let's say the pulling force. Let's say in the lab, we just know how many Newton it pull then until it's broken, correct or not?
And when pulling also, because we don't know what is the adhesion between the two different materials. Two different material at the interface, they have some certain kind of, adhesions force. We don't know that one. So when you see the what you show here, when we pulling actually is like separate. These two material, it will separate on the interface.
Okay, one question. Let's say in the lab,
maybe it will break. It will like break like this. We don't know, because if you check, like when they are installing the fiber optic also, they just once they pull, usually the jacket, right, the outer the polymers, the what MDPE polymers, they usually break first one.
yeah, I believe also true, right?
Usually it will break first one.
Okay, one question. In the lab, let's say you use the machine to pull, so what measurement parameter we can check from that machine usually? Is it Newton, applied force, or what?
Force, it will be like Newton divided by the area, the cross-section area will be mm square usually. So the result will give you in terms of megapascal.
So
but the result give you is for the whole cables, the whole thing.
The machine will know how many cross-section area, or with the key in the
we
value?
need to key in. Usually this one is the number we need to key in.
Oh, the cross-section area from the top
the
this
machine
side,
will detect how much is extend. How much your cable become longer, and the machine, it can detect how much force is already applied.
So let's say compared to the simulation, so what parameter we can take from the simulation to compare with the laboratory test that you mentioned? Stress. They mean this value this value.
The maximum stress.
The maximum stress, the red color, for example.
Yeah, the red color.
With different force, right? We have to apply different force in the simulation also, right? So compare with the lab, right?
Don't need. The force is depend on what is when during an application, how much force you apply.
Yeah, this is also is our question. Actually, we also don't know what is the maximum Newton so far. So let's say in the lab we try to pull out until it's broken, right? We have the maximum force also. So we key in the maximum force in the simulation, so we can compare.
The force,
maybe
the force in our lab, I think is fixed, is 50 kilonewton. The load cell we have is only one type of load cell, and then the force can generate from there is 50 kilonewton.
I think it's quite high also, like 50 kilonewton. Many things can be broken.
Metal also can broken.
Yeah. You mean for the pulling force, right? No, actually, this is okay. What our objective is very simple. We want to make sure our simulation, let's say pulling force, when we start to deform or broken, with some Newton here at the left hand side, we say some Newton, right? Then it's similar to the lab test, same 50 cm. Then when the pulling force in the lab is let's say until 15 Newton, we start deform, and we say it's same with the simulation.
But the simulation, it won't show you the material it will break.
Yeah, last time you said that you have to determine on the use strength, right?
That one is just
You have to find out the use
that one
strength.
is just tell you before it's deformed, how much stress before it's deformed. Yield stress is how much stress happen on this your design before it is undergo plastic deformation. Let me have
Yeah. So what is your suggestion? How to achieve our objective? So mix
if you want
some
to,
sand to so that our simulation is compatible with lab test.
if you want to do until break, that one will be
Or not that until break start deform also can we just
deform.
anything you say or break also can. I don't know. I just
We can check the years. We can try, but I'm not really sure it's correct or not. We can get the year strength from the data also. And
use strength from the data sheet, right?
Yeah. Can the from the stress strength curve you can obtain.
What curve? Sorry.
From the result, what you obtain, we call it a stress and stress versus strength. Stress versus strain curve. From that one, we can look for the tensile yield strength .
Or maybe later on you show Marina how to get the curve.
And the one from experiment result that
you mean is from the lab test, you mean?
Yep.
Oh.
It will show you a graph also. You will see how is the pattern, the fracture pattern of the specimen.
Oh, you mean the stress versus what?
Strain.
From the lab test. So we can compare with simulation.
STRAIN. Strain. I think ST. A. I put in the chat.
IN. Strain. Stress versus strain. Right? So this one can be do in the laboratory test.
The software it will show you.
Software also will show, right? Lab test. So you mean we can compare this this one in lab test and as well as the software.
The graph you can obtain the yield strength.
Simulation and no, they mean if we use the simulation also can obtain this graph?
No, because what we simulate is elastic behavior. We did not simulate the plastic.
So how to compare to simulation?
This one we just obtain the yield strength.
This one can obtain the yield strength. Yeah. This one you obtain the yield strength, then we compare the yield strength in the simulation. Correct?
But actually, usually a simulation and the reality result, it will be different one. But
yield strength is a material that is start to deform, right?
Plastic deform.
Right? But my question is like this. When we do the simulation, we only can see one material yield strength only. For example, we have a jacket. So once the machine do the simulation, you only can see the jacket. Let's say we have the data sheet, yield strength is 500. Then when she try to apply the pulling force, we only can see one material. What is the maximum stress? Maybe 300.
Actually, you can check. You can how to check?
You can check every component. Can we check the overall component?
Okay. I'm not sure. Actually, can check. We can like plot one line. Then at that line, we can have how we say we can have a plot. Maybe you point on the particular location. You able to read the stress.
The stress of overall, you mean?
Or no, a particular location. let's say you want to see that location, you just like use your cursor, just point, it will show you.
I mean, or you mean location is this point? What is the bus?
Yeah.
Uh, do you mean that, let's say in the lab test, right? So the lab test, the result actually show in particular point of the jacket only, right? Let's say it is 50 cm. So actually, the lab test result is show the result at the particular point or overall. This is my concern. The simulation result is
Oh,
show
okay.
particular or overall. So how to matching with the lab test? This is my question. That's why I
But
asked
the
you.
lab, the lab also did not like specific test for the one particulars. I mean, specific test the mechanical properties for the specific location.
Yeah.
The one also we check the overall.
Yeah. I think overall. So that's why my question is, in the simulation using the SolidWorks, how we check the overall use the span here, the span of the simulation.
Usually we will check the
This is one by
highest
one only, right? This
just check
only
the
one material, you see. So one material we know,
just check the
okay.
location where is having the high stress.
Yeah, for particular material, right, one time one only, right? Correct or not? Let's say in the marine, inside have cable, have steel. So let's say you apply the pulling force. So what we can know is only just let's say jacket only. We only the jacket we know what is the stress in the particular location only. But let's say you want to check for steel, you have to click on this and another caption, right? Like this, correct or not? We just can check one by one only, right? Correct? And also you ask Marine to select all the surface, right? You see Marine simulation, he just choose one particular surface, not all the surface, right? So I'm just curious. Let's say she choose all the surface, then you pull all. At the end also we get the separate result only, right? Correct?
Just selected the steel wire, sir, because steel wire is a fixed one. No. That's why I selected only the steel wire.
Yeah. So as mentioned by Dr. Kui, you have to select all, not only steel wire, right? Then later on you show to Dr. Kui, Dr. Kui will correct you.
Maybe one more questions if like if maybe if SolidWorks really can only show one I mean one data one by one if even though if you select all if only show one by one, is there any formula to calculate the overall by combining all the data that we have? Maybe there is a way to calculate that. Is it possible? Just asking.
Hmm.
Marine, you copy down what we have discussed, the conclusion or what? So you take note. Although I will record this video, but I hope you write down is better for you. You remember the important
I'm
things.
writing.
Okay, good. maybe if Totoko you don't have the answer now, never mind. If you have answer in the future, you let us know. Just post in the WhatsApp group. Marine, I think you can share your simulation. So let Dr. Kui have a look. I stop sharing. You share now.
Yes, sir. Can you see my screen, sir?
Yes, screen.
I can see.
So, yes, sir. I will apply the force now, sir. This is the
Include all the
model,
material or not? Only the ticket only.
all the materials, sir.
Part 1, part 2, part 3. Okay, okay. But what all the color is same? Oh.
Mostly the fiber colors and everything are in the same colors.
Yeah,
Sir.
because this one is software, right? You assign material, the appearance, we did not assign the appearance.
Yeah.
That's why the colors is look all identical.
Yeah.
If you want to differentiate it, maybe you can
Edit appear.
you just put the edit the appearance.
Oh, never mind. They just try to. Okay, you do step by step. Let Dr. Kui to check examiner. See you do it correctly or not. Yeah.
So this is the design. So when I am doing for simulation, so you asked me to like fix the one whole face, no, sir?
I mean, yeah, all the face.
So I'll fix the bottom face. Is this correct, sir?
How about the jacket?
Yeah, I have selected the jacket, sir. Okay, sir. Okay, sir.
Yeah, okay.
Shall I give it as 100 newtons, sir?
Select all the face. Have you select? No, not the face. I mean on the face, not the side. I mean all the face on the top.
Oh,
Okay, the face is different from the previous one.
oh.
Just now you
So
select the button on the top.
This is for the top, sir.
I mean, just now when you select the fixed support, you select the bottom or the top.
Bottom one, sir.
Okay, this one then you select from the
Yes,
top.
this is the top face. So the face will be applied for the jacket only, no, sir, not inside, right?
So mean that the box like that, all the face include the steel, helping member and optical fiber, right? Oh, I mean, for the applied force, you have to click all the face aside, the fiber optic, jacket, FRP member, and so on top.
All the member inside you need to select.
Yeah, just Marine, you know common sense or not?
Yes, sir.
You're a PhD student already. Okay.
So, okay, sir. I've selected it.
Yeah. Then how many force that you're going to apply?
100 Newton, sir.
And then you need to make sure the directions, you need to select the direction. You can see the direction of the force is different. You need to make sure the direction of the force is perpendicular with your selected face. So you can check on the direction, yes, yeah. So you can see the direction, which component you're going to select.
So for everything, it will be upwards, no, sir.
Yeah,
The
just
force.
perpendicular.
So this is right, no, sir. This upward direction, like.
Why your force, you assign two direction of force. For other direction, if you don't want to force,
Is this
yeah, only one direction. Yep. Only 1 Newton? Maybe you just put like 100 Newton and see.
some mesh is like default? Should I give okay,
I
sir?
just use the default one. It's okay. If you put very fine, later on when you calculate, it will take a lot of time.
So what's
You just click OK. Maybe you put a smaller size. You try to create the mesh. Go to mesh, right click, create mesh. You can use smaller fine mesh and see what happens. I use fine.
5, sir?
Fine. You see cross and fine. You just no, don't do fine, too fine. Go backward a bit. Okay, stop. Okay, you just continue to see. Okay, can run the simulations.
Creation failed for following.
Not running mesh, reducing overall size, adding mesh control. You try to run the diagnosis and then see what happens. This one I'm not really sure what happened. First thing, maybe I will suspect because of the mesh. The other thing, maybe the connections, the contact between the components is not defined. So maybe the simulation it cannot run.
Design, sir, like the mating, the connection, like the parts mating.
Yeah, the components contact. Maybe the connections, the component contact not defined also, probably it will cause this error.
Marine, or you try to show pulling force for jacket only, see can or not? You can try like this.
So I'll delete this one, sir. This study.
Oh, never mind. You let Dr. Kui to take control, then last time you say can set the what connection, right? Just simply put some connection for every component, then see can or not. Or Dr. Kui don't try. I mean, Dr. Kui, do you want to take control Marine computer?
Send me your file, then I check. I'm also not sure because if I want to check, so maybe it takes some time to check.
Okay.
In very short time.
So Marine, you send sorry, Dr. Kui for this. You send the whole file to Dr. Kui. You zip it and send to Dr. Kui.
You just zip it and then you just send me. Because if I run also, I need to have some time and then check what happens.
Sure.
In very short time, very hard to conclude and then give you a feedback.
Sorry. Okay, Marine, just now you show in the WhatsApp group, you just push one of the material only, right? Can you show us?
Like I fixed.
Yeah. You try here. You fix what? You fix the steel.
I showed you. So you won't need to make connection in this one. Did I do something here? Because I didn't do anything.
Yeah, maybe You open the video of Dr. Kui last time I sent to you the
connection. What I did is like we have one option called as mates, so we can like connect the different part inside the component using mate. I did that one, sir.
I can't hear you clearly. Maybe Dr. Kui can give suggestion on this one. I'm just sure.
The mate just for the assembly, but the connection is actually need to set like what is the interface properties. I mean, what is the friction force between them? It's okay. Maybe after the meeting, you just send me a file. So when I'm free, I check and then see.
Is it like rigid connections for everything? Because spring pin and everything is other.
You leave this first, please.
Yes.
Okay, so how the apply the force on the top, right? You see a Marine design, the top is not the surface is not it's not flat. So how to draw the line so that we can apply the force? Oh. Okay, can you all hear me now?
Can.
Okay, let's say we want to apply the force at the top. So how we draw a line on top of this? Because you see this cable, you can see from the front it's not a flat. So we can show here or take example if you want.
I think Dr. Man, I think better let the students send me the file first.
Okay.
Then let me try first. Let me have some time and then try first. So if I have any finding, then I just can feedback. I need some time to try on this.
Yeah. So okay, good lah. Let's say Dr. Kui had found it how to do it. Maybe we have another Zoom meeting. Maybe Dr. Kui show to Marine.
Just give feedback in WhatsApp group also.
Can also. You can give them WhatsApp group. So from my side, no any questions. So Marine, anything you want to ask?
No, sir. I will try doing these connections and I'll update the group, sir. And also I'll
maybe
check.
you maybe
I'll-
you double check whether you define all the material or not.
I
Properties.
didn't. So
You double check whether you define all the mechanical property for all the components or not. Double check all this. Can you hear me?
voice is breaking, sir.
Yeah. Never mind. Maybe my line is not too good now.
Now I can hear.
Okay. Yeah. Never mind. You just try to solve the problem, and also send the file to Dr. Kui. And for the mechanical property that is still absent, you try to figure out what is that. Just now at the beginning of the meeting, I showed you already, right? Some property is still not finalized, like FRP, for example. Correct? No? Some still don't have use strength and so on. Then we meet it again this Friday for Marine and Cognac. Right? And how? Any questions from you? Wait.
So no, sir. Like I'll send the file and I'll
Yeah.
check how to do the connections, and I'll check all the parts also, sir. Like the
Yeah.
mesh was not working, so I'll check that
Yeah,
also, sir.
yes. Good. Okay, thank you, Dr. Quick. Sorry for bothering you, and you give very valuable suggestions and help us very much. And Maureen, you have to really appreciate help from Dr. Quick. So you have to work hard on this and try to do the best. And when you come back to Malaysia, okay, you have to really thank you, Dr. Quick, for this. Hope you take care in India now and keep focused and do your work, keep your momentum. Only then you can achieve your goal. So I think I will end the meeting now. Thank you, everyone.
Thank you, Dr. Kui, for your time. Thank you so much, sir.
Yeah. Okay.
Thank you, sir.
Okay. Bye, everyone. We'll end the meeting now. Bye.